Okay, so do this lecture 12. Talking about the last lecture, we tried to cover the following topics: application of biosensors in the diagnostics industry, particularly for metabolites of interest like urea, creatine, oxalate, glucose, adenosine, so on and so forth. There are different gas-based sensors which are used for taking blood sample, doing quick analysis of one or more of these metabolites in the patient's blood sample. And essentially we also tried to investigate little details about how the double layer between two phases of solids, or solid and a liquid, or liquid and a liquid, formulates, and how there is a charge separation which would lead to a distribution of one phase as a counter ion charges as bulk charge or diffuse layer within one of the phases, one of the interacting phases. So now we would look into, and so we actually try to find out also the potential in a one-dimensional model of an electrode in contact with a solution, and try to estimate the value of the potential from by solving the one-dimensional equivalent of the Poisson's equation for electric field, okay, for potential. So essentially we got the density factor, the charge density, volume charge density rho, equated to minus a d square of k e to the power of minus kx by 4 pi, right. D is the dielectric constant, I am sorry. K again is a constant which was put as an equivalent of the total amount of charges, e to the power minus kx. X is the direction in which the potential has to be evaluated. Let me just write this a little more clearly here, make it x, okay. And a of course is the constant in the solution of the potential equation with respect to x. So if you really look at the surface charge density, and we also try to discuss this, that in the electrode a very critical parameter of importance is what is the charge density on the surface of the electrode. When we are talking about microflows, microfluidic channels, the charge density essentially means the density of the dangling bonds which are there on the surface. If you have a silicon surface and you salinize it and get it converted into SiOH, and then under a certain pH this converts into SiO minus, the charge density on the surface of such a situation would essentially be a function of the bond density on the surface too, okay. So now if you look at or if you assume sigma to be the surface charge density of an electrode, okay. So the relationship between sigma and rho would really be sigma is integral minus of course rho times of dx, okay, where x varies between a and infinity. One thing which I would like to illustrate here is how this equation is coming out is from the fact that if you look into the principle of electrical neutrality, the charge which is there on the surface of the electrode is should be equivalent to the total amount of charge in the volume of the solution which forms an interface with this particular surface, okay. So with that logic, the surface density should be the negative of the volume charge density of the solution, and integral of that with respect to the distance x from the electrode. And if you may recall, the outer Helmholtz layer is at a distance equal to let us say some value a, which is the ion size parameter. Also we can consider that to be what is the beginning of this let us say this so called solvated ion shell, and then beyond that the potential extends all the way up to infinity, and so there is always a density of charge mathematically possible up to infinity. So the charge density goes down of course with the increase in x, but it is never almost 0. It goes to a certain finite amount which is close to 0, okay. So with that logic we can say that sigma is minus rho dx integral where x varies from a to infinity. So if we put the value of rho here from equation 2 and try to solve this equation, we are left with sigma equal to ad times divided by 4 pi integral e to the power of minus kx dx integral varying between a and infinity. I just want to recall that, I would like to recall that a is the ion size parameter. So, if you really have an electrode with a negative ion, say here, and there is a plane here which contains all these different positive charges on the outer Helmholtz planes, okay, and as it goes down, the density slowly reduces into the bulk volume, and this distance is x. So, the x really starts from where the solvated ion shell, which is somewhere here, starts, which can be equivalent to the ion size parameter here a. So, from a to all the way to about infinity, we can find out what is the charge density by looking at really the rho, the volume charge density, and maintaining what you call the principle of electroneutrality. Okay. So, these are all positive charges, and these are all the solvated ion, solvated shell of thin water molecules. By the by, this layer is only about tens of nanometers. Okay. So, it is extremely small, tens of nanometers. Give me a minute here. About 10 nanometers. So, if you solve this integral here, you are left with a d k square by 4 pi integral a to infinity e to the power minus k x by k, of course with the minus sign, and this would eventually convert into a d k square by 4 pi times of e to the power of minus k a by k, or in other words finally converting into a d k by 4 pi e to the power of minus k a. Okay. That is what this is, and from that we can estimate by looking at the surface tangency sigma the value of a, the coefficient in the solution of the Poisson's equation. So, a here would be represented as 4 pi sigma divided by d k and e to the power of k a. Okay. That is how a can be represented, and essentially the potential function x, which is also a e to the power of minus q x, becomes 4 pi sigma by d k. D again is the dielectric constant of the medium in which the solution is present. So, the solution normally is in an aqueous medium, and so the medium is water, and dielectric constant would be the dielectric constant of water in CGS units. So, 4 pi sigma by d k e to the power of k a minus x. Okay. That is what the potential function phi x would be. Interestingly, it would be almost a very good thing to assume what the potential would be just close to the surface. Okay. Just close to the surface means where the ion size parameter for the negative ion ends almost. Okay. So, it is very close to the electrode surface where the solvated ion or solvated shell of these thin water molecules, tens of nanometers, they just about start, and there is where the a actually ends, right, the ion size parameter ends. So, at that particular parameter, the potential that is available really is nothing but the surface potential of the particular surface, okay, in question. And so, therefore, if we put x equal to a in this particular equation for the potential, equation 3, we should be able to get that as an estimate. So, let us look at what the potential function would be at x equal to a. So, it should be equal to 4 pi sigma by d k e to the power of 0, okay, or 4 pi sigma by d k. Okay. So, this is also the surface potential close to where the solvation cell just about starts. So, this is the surface of interest, and this is the solvation shell of water molecules which start in this particular region, and this is, let us say, the positive charges in the solution, and there is a reduced order of these charges as it moves more into the bulk, and essentially goes all the way up to 0. And so, the electrode here is negatively charged, and the ion size parameter can be somewhere very close to the surface. Let us say it is a. So, between a and x equal to infinity, there is a charge distribution, but at A the potential really is the surface potential. So, this concept should be very clear in mind, because this we need to use or will be using very often for determining what you call electrokinetic flows in some of the next modules. All right. So, what we call this zeta potential or zeta of phi at 0. So, we call this the zeta potential of a surface. There are ways and means now of measuring the zeta potential of a surface of interest. Okay. Initially, for any solid surface, the zeta potential would be a very hard parameter to find out, but there are meters now available where this measurement can be made. Interestingly, also for nanoparticles, okay, particles whose sizes are less than 100 nanometers, the surface potential forms a very interesting aspect, because it always is a result, or it always is leading to the discretization of these particles, and it always prevents aggregation. So, a very important aspect in making nanoparticles is how you can change the zeta potential of the surface, and you can use variety of surfactants or a variety of materials which kind of coat the surfaces in a manner that you have a certain potential associated with the surface, and if you have uniquely similar potentials across all the other nanoparticles which are available, they hardly coagulate. Okay. So, just to give you an idea of how important this zeta potential is, whether it is a plane surface or the surface of a nanoparticle or any other surface, okay, zeta potential of an extreme importance. So, with this we kind of have a very good idea now how a surface would behave with respect to a solution. I would now go to directly almost into the various electrokinetic phenomena that are available and that can be used for a lot of microflow related situations. Okay. So, what are those electrokinetic phenomena? Okay. So, let us look at some of the definitions in order to begin with this new topic, and it is very much related to the earlier topic on zeta potential of a particular surface. So, electrokinetic properties are associated with phases in contact with each other and are of particular significance for microflows. Okay. So, whenever there are two or more phases which are in contact with each other, there is almost always these properties of charging which comes into picture. So, one or more of these interfering or participating surfaces, interfacing surfaces develops some kind of a charge. Okay. So, applying an EMF across such an interface causes movements of all the phases with respect to one another, okay, while force movement of phases produces characteristic EMF. Okay. So, thus the cause and effect are interchangeable, and altogether all electrokinetic effects can be summarized as either motions caused by imposed EMF or EMF produced by the movement of phases. Okay. So, in one cause or in one kind of phenomena, you impose an EMF or put a potential or subject a potential and try to study the flow or the motion to the charges or the charge separation of the double layer which happens. Okay. In another instance, you are basically producing an EMF by forcing a certain interface over another which develops this dual layer charging. So, there are 4 different mechanisms which can be categorized into these 2 subtypes. One is motion caused by the imposed EMF. This category involves, or it includes electro smashes. Okay. And definitionally, electro smashes is really principle by which liquid caused to move through a static diaphragm with microcapillaries across the diaphragm occurs. Okay. So, due to electro smashes, it generates some kind of a driving pressure which causes liquid to move automatically through static diaphragm or a set of microcapillaries. So, we will investigate this process a little bit in details in the following slides. The other phenomena of motion caused by imposed EMF is really a motion of charged particles in a medium, okay, on subjecting to an electric field. So, this is also known as electrophoresis. Okay. So, solid particles caused to move through a stationary liquid when it is subjected to such an external EMF or such an external electric field. The other 2 phenomena of importance, and these 4 phenomena are really important for sensing and microfluidic applications, is basically those which are categorized in the subtype of the case where EMF is produced by forcing using pressure driven flows one fluid or one interface on other surface. So, one such phenomena is called the streaming potential. So, it is a potential produced by liquid being forced through a diaphragm or through a set of microcapillaries in the diaphragm. Okay. So, if you are forcing this liquid phase over a solid phase essentially with some kind of a diaphragm which has all these microcapillaries. So, you are forcing them with several microcapillaries, it causes a potential because of the flowing fluid. It is also known as the streaming potential. The other important effect is sedimentation potential. It is used very often in the chemical industry. So, this is the potential produced by the free fall of particles through a liquid. So, this is a gravity driven fall of particulate matter in a liquid which would cause a certain amount of potential, and this can give information about the weight of those particles or the rapidity with which they would sediment or settle down. So, this is also known as the dawn effect. Okay. So, we would be more interested in studying just a few types, actually these three in more details, about how a motion can be caused by EMF or a EMF can be caused by motion. Okay. So, let us look into a little more details of the first process, that is electro smashes. Okay. So, by definition, again a diaphragm through which a liquid is forced may be regarded as comprising of a series of microcapillaries. Okay. So, we have a situation here where you are pushing fluid through a set of microcapillaries. Okay. So, let us look into this first process, electro smashes, and as you know, by definition electro smashes really is a case where liquid is pushed through a set of microcapillaries. A diaphragm, it can be considered as a bunch of different microcapillaries through which a liquid is forced into. Okay. So, this around the internal surface of these capillaries there exists a double layer of separated charges because of the flow of fluid which is pushed through this set of microcapillaries. So, this situation can be represented here, as you can see in this figure here, that you have a flow which is of this water, and this is, let us suppose, the span of the capillary. Okay. So, this essentially is the span of the particular microcapillary into question. Okay. Let me just put it a little more appropriately. From here all the way to here is what the radius of the capillary is. The length across which we want to investigate this dual layer charging is, let us say, L. Okay, from one end to the other end of the capillary. So, what would happen immediately is, as you know, that these are pressure driven flows and it causes a no slip zone. So, very near to the surface in this particular area or region there would be a zero velocity. So, there is a plane of no slip. Okay. That is true for this other end of the surface as well, where there is no velocity or there is no slip between the fluid layer and the liquid. Okay. Now, let us suppose the dual layer really formulates a little bit away from this particular positively charged surface. Let us suppose that the charges on the surface are all positive in this particular case, and the dual layer is formulated by this negative charges which almost always comes into the solution and extends back into the bulk. So, you have to be careful though in this case that, you know, positive really means electron less. Okay. So, there are the surface is devoid of electrons, whereas negative in the solution would be always in ionic state. So, the ions are almost always bigger than if there are holes. Okay. So, the same phenomena would happen if the electrode is a positively charged electrode and the surface or the solution has negatively charged ions. Whatever is in the solution is of a bigger size. If you consider the charge equivalence, there is almost always the formation of a diffuse layer, because whatever is in the solution, whether it is a positive charge or a negative charge, is always going to be of bigger size. If the electrode is positive, it is by positive by virtue of the electron, because it is electron devoid. Okay, by virtue of it being electron devoid. So, essentially it is a hole, it is an electron less state. So, therefore, there is no way almost that you can neutralize the total charge, whether it is positive or negative, on the surface of the electrode by the charge that is in a solution. Solution charges are almost always of finite size, whether it is a positive or a negative ion. A negative ion is much bigger than the but then the neutral state of the species itself, okay, whereas positive charge is a little smaller, but then it is no way comparable to the size of an electron. Okay. So, there is almost always the development of this diffuse layer of charges. So, here we consider let us say an EMF which is applied external to this capillary. So, there is an EMF because of by virtue of this battery which is applied, as you can see here, by means of a series of batteries in the circuitry. So, what do you think will happen? There would be a tendency of these negative ions to move towards the positive electrode, right. So, as the fluid is moving in this particular direction with V, and it has occupied the whole capillary, and after that let us say we have removed the pressure, and so there is no driving of the fluid anymore. And when we apply the EMF, the negative charges should start flowing towards the positive of the battery, right. And let us assume that the velocity of flow in this case is V. Okay. So, let us say that the velocity of flow in this particular case is V, okay, because it is a negative charge and it is flowing in the opposite direction. This velocity is V. So, from a point of no slip very close to this surface, this particular outer Helmholtz layer where the first line of charge, the counterionic charge, comes into existence and the solvation layer has just ended, moves at a velocity V. So, the velocity gradient here, okay, if we assume the total double layer thickness to be delta, so the velocity gradient is essentially V by delta. All right. We know for Newtonian fluids, the shear stress which develops between the different layers is actually equivalent, or it is proportional to the velocity gradient du by dy in this case. Okay. And the constant of proportionality there is nothing but none other than the viscosity of the medium, the neta. Okay. So, that is what Newton's law states. Let me write this a little more clearly, viscosity into the velocity gradient. So, let us think about this case here where this particular Helmholtz layer has started moving. So, before it got to start to move, it would have to undergo the necessary shear stress, okay, to create this velocity gradient V by delta, right. So, essentially we can calculate that this in this particular case can be represented as neta times of V by delta. So, this is the amount of stress that is needed, the amount of stress or amount of force per unit area that is needed to shear the outer Helmholtz plane with respect to this layer of no slip, okay, which is present close by as the inner solvation cell close to the surface. So, you have single molecules of water which is very close to these bunch of positive charges, and that is the inner solvation shell which separates the counterionic cloud, the negative counterionic cloud, from the positive vacancies on the top of the electrodes. And so, V by delta essentially is the velocity gradient, and neta times of V by delta is what the shear stress would be for such a layer separation to occur when the fluid starts moving. Okay. So, let us assume also a potential gradient, and if the length here is L and you have applied a voltage between these 2 points, same as the voltage given by the batteries here as E, then the electric field in that case, the potential gradient, which is also the electric field, okay, electric field is E by L. Okay. E is the EMF. You have to remember, this is not the electric field, but the EMF, the voltage that is applied between the 2 points of the capillary. Okay. So, this end and the other end here of the capillary. So, that is what the electric field really is. Let's Let's delete this portion away. That is what the electric field really is, okay, between these two ends. So, this can be represented by some term x here, all right. So, in order for the potential gradient to move the fluid, the shear stress should really be equal to the electrical force to the charge per unit area. So, let us suppose the charge density on the electrode surface, in this case the surface of the channel or the microcapillary is sigma. So, sigma times x really is nothing but the electrical force to the charge per unit area. Let us assume, let us try to imagine the dimensional consistency here. Sigma here is charge per unit area, it is the surface charge density, and x here is the electric field. So, electric field, which is x in this case times of charge, is the force, and so this is force per unit area. So, in order for this layer to be mobile, the total amount of electrical force per unit charge area to the charge per unit area which is needed would be equivalent to the shear stress that would allow the separation to happen and the fluid in the microcapillary to move ahead. Okay. So, all said and done, we can find out a relationship between sigma and all the other parameters at n v by delta x here, and also from the earlier derived equation on zeta potential that we had found out just about few slides back, zeta came out to be equal to 4 pi delta divided by d times of sigma. Okay. Delta here, if you may recall, was the total, the thickness of the diffuse layer, right, and d here was the dielectric constant, sigma was the surface charge. So, in terms of zeta potential, we can very well write this particular equation as 4 pi delta by d times of neta v by delta x, right. So, these deltas go away and we are left with 4 pi neta v by dx, which is the zeta potential on the surface. Okay. So, the velocity of flow in this case v would really be equal to nothing but zeta potential times dielectric constant times the electric field, external electric field times of divided by 4 pi into the viscosity neta of the medium. And if we assume the field to be 1 volts per centimeter, or we assume an electric field of unity value, then we are left with a velocity which is also known as the mobility of electroosmosis or the electrosmotic mobility. Zeta d by 4 pi neta. Okay. So, it is essentially the velocity per unit electric field. So, it gives an idea of how mobile the liquid phase within the microcapillary would be by this principle of electroosmosis per unit field, external field that is applied to the capillary. This is also known as U0. Okay. And we can further do some analysis, because when we talk about microflows and capillaries associated with these kind of flows, we need parameters like the flow rate. Okay. And velocity essentially is nothing but the flow rate per unit area, as we all know from our fluidics background, right. So, volume flow rate Q divided by, let us say, some area would represent the velocity. So, here also if we assume phi to be the flow rate, the volume flow rate, let us say volumetric flow rate, and let us say small q to be the area of cross section of the small capillary. Okay. So, therefore, V essentially is q by phi by q, right, and that comes out to be zeta dx by 4 pi neta. So, this is how you can represent in terms of flow rate and area of cross section in any microcapillary the relationship between the mobility and the flow rate and area of cross section. Okay. So we can further make it or change this equation to gauge the zeta potential, zeta, as 4 pi neta phi by dx times of q. Okay. So these are all measurable quantities except this x here, which I would just be changing in a little bit, and zeta essentially can be found out from this equation for any surface in combination with any liquid. So that if for a certain common material of two interfaces, we can find out the zeta potential by this method, where neta is the viscosity of the liquid phase, phi is the flow rate which is obtained because of electro smashes, d is the dielectric constant, q is the area of cross section of the capillary, microcapillary, or the channel through which all this flow is taking place, and x here essentially is the field, and we would just in about a little bit see how this field can be predicted in terms of current per unit the conductivity. Okay. So as we know from Ohm's law, the way that resistance is defined is rho L over A. Rho is the specific resistivity, L is the length, A the particular medium, A is the cross sectional area of the medium between two contacts, okay, of which the resistance has to be measured. Now this can also be written down as the inverse of K, the electrical conductivity, times of L by A. Okay. So this is essentially the electrical conductivity, it is the inverse of electrical resistivity, which in this case would be close to, so we can change it a little bit. So K here can be represented as L by Ra, okay, length by radius into area. And what is resistance really? Resistance is nothing but the EMF that is applied divided by the current that is created, right? That is how you can have the resistance. So this is sorry, I just made a little typo here. So the resistance is the EMF by just by Ohm's law, the EMF divided by the current I that is created in the particular medium. In this case there is a small thin liquid column within the microcapillary, and you are creating or you are measuring the current I as you apply an external electric field E. So E by I is the resistance in this case, right. So essentially again as you know, E by L is X, right, and area here is nothing but let us say pi r square. You assume that r is the radius of the thin microcapillary, okay, and I is the current, and length here is always accommodated in this X factor. So K, the conductivity, is essentially I divided by X pi r square, or there is a way that we can express X as I by K pi r square. I could put this back into equation 4 here, which we derived, and that way zeta can come out to be 4 pi neta phi divided by d times of I times of q, which is actually equal to pi r square as we assumed in this other expression, divided by k times of pi r square. Okay. So we remodify it a little bit and make this 4 pi neta k phi divided by d into I. Now I would like to draw your attention to that, to the very fact that these are all measurable quantities. You could measure the current value, the dielectric constant is almost always known, K is a property of the medium, there are standard tables for that, phi is the flow rate, N is again the viscosity, is again the property of the medium. So with all these different properties or aspects of the medium and measuring the the flow rate per unit current, you could always gauge what is the zeta potential of a particular surface, and this is of immense importance in electrochemistry as well as microfluidics. The way that zeta potential changes affects a lot of behavior. Okay, so so this kind of gives us a way out of trying to analyze electroosmotic flows within microcapillaries. Now let us actually also, for a comparison's sake, try to compare it what would happen if these capillaries would have pressure driven flows. Okay, so essentially we start investigating these microcapillaries with Navier-Stokes equations for different situations of pressure driven flows. So before doing that, just to illustrate a little bit of conceptual things, we would investigate the Couette flow, which is essentially between two dimensional plates or surfaces, parallel plates at a distance of 2h, which has a fluid in between. Okay. So, let us draw this out. So, this is like you have two surfaces, surface 1 and 2, and you have a fluid in between, and what you are doing is you are trying to move this surface at a velocity v. Assuming there is a no slip zone, the fluid kind of develops a velocity profile starting from 0 here, v equal to 0 here, all the way to about, u. Let us say the velocity of the fluid is a parameter u for convenience sake. So, you have u equal to 0 here because of this zone of no slip, and then the velocity slowly increasing to u equal to v, the velocity of the plate here. So, you have a zone of no slip here, you have a zone of no slip here. So, you can assume it as if this zone of no slip leads the fluid to move integrally as one part, fluid layer to move integrally as one part with the plate, and this zone of no slip kind of rests it back, and there is a velocity gradient which is obtained. So, let us assume this to be u y, okay, as a function of y. So, where y varies between plus h and minus h, we place the coordinate system in a manner so that origin is somewhere in the middle of the plate, between the plates. So, this is the x y direction, okay. And so, we use the Navier-Stokes equations to get an idea of the velocity profile or the velocity equation. As I told you earlier, we will be only discussing the conservation of mass and conservation of momentum equations for microfluidics. Okay. So, for the conservation of mass equation, we get du by dx plus dv by dy plus dw by dz equal to 0. V and w do not make any sense because we are assuming the v and w to be 0. There is no velocity along the z direction, which is, let us say, into this plane, and also along the y direction. So, there is really no circulating flow in the whole of this domain. So, there is only a unidirectional flow, and u is basically non-zero, and also a function of y. The way that it varies, the u varies, is a function of y. Okay. So, essentially this and this terms would be 0, and so we are left with du by dx equals to 0 in this particular case. Similarly, if we apply the momentum equation, so applying the conservation of momentum, we have rho times of, so we have rho times this u du by dx plus v times du by dy equals minus pressure gradient dp by dx plus this inertial term rho gx plus viscosity times of del 2u by del x2. This is the shear term really, del 2u by del y2. Okay. So, here as we know v is 0, as we had made in the assumptions for the coed flow, and du by dx has already been obtained to be 0 from the earlier conservation of mass equations. We assume there is no pressure gradient, it is just a movement of fluid trapped between two plates with one moving, one fixed, and there is no inertial component of the flow. Also, d2u by dx2 is 0 because du by dx itself is 0. So, therefore, we are only left with neta del 2u by del y2 equals 0. Okay. So, solution for this equation would be y equals c1 u equals c1y plus c2. Okay. So, that is what essentially del 2u by del y2 equal to 0 would mean. And now we evaluate this particular equation under the boundary conditions, where we already know that for y equal to minus h, u is 0, and for y equal to plus h, u becomes equal to v. Okay. So, from the evaluation of this equation, we really find out u essentially as v by 2h times of y plus v by 2. Okay. So, this is the case of the co-wet flow. We also want to determine what happens if you have a pressure gradient which exists between these two flows, and then essentially we want to plot the flow profile in that case and compare it with the flow profile of a electrokinetic flow as we have seen earlier, the electroosmotic flow as we have seen earlier. So, here in the other case we have this the pressure driven flow where in this particular case both plates are fixed. And there exists a finite pressure gradient. Okay, that is why it is pressure driven. So, essentially you have two fixed plates, this is fixed and this is also fixed, u as a function of y in between, and so really the from the conservation of momentum equation can be written as rho times of u del u by del x plus v times of del u by del y equal to minus d rho by dp by dx dou x, which is actually a finite amount, it exists in this case, plus the inertial term rho gx plus eta viscosity times of this is the shear term del 2 u by del x 2 plus del 2 u by del y 2. Okay. So, just from the conservation of mass equation, as we know already in the earlier slide we had seen that du by dx in that case is 0, right. So, this component is 0, there is actually no v which exists in this particular case, is again a unidirectional flow, we only assume flow along the x direction. So, there is a velocity along the x direction, but along the x direction as you see by the conservation of mass there is no variation in u, the u only varies in the y direction. Okay. So, there is a finite pressure difference in this case, this is really not a non-zero term, we assume no inertial effects. So, rho gx is 0. By the way, one of the reasons why no inertial effects are assumed in case of especially microfluidics or microchannel flows is because the volume of the mass that is involved is pretty low. Okay. So, therefore, the inertial effects sometimes are really not that significant or that prominent as its corresponding macroscopic counterpart. So, microfluidics we normally assume until it is absolutely needed, we assume the inertial part of the flow, the gravity term of the flow to be kind of negligible. Okay. And so, we are left with again d2u by dx2 is 0 because du by dx itself is 0. So, we are left with d2u by dy2. So, in this case the equation takes the form eta del 2u by del y2 is equal to del p by del x, okay, the pressure gradient. So, there is a finite pressure gradient in this particular case. So, if we just try to solve this particular equation we are left with solution for u which is equal to neta, which is equal to 1 by 2 eta del p by del x pressure gradient times of y square plus some constant c1 times y plus c2. Let us investigate in this particular case what happens. Really, if you have a central axis here and y equal to 0 here, and we assume y equal to plus h as the location, spatial location of the upper plate, and y equal to minus h as the spatial location of the lower plate. In that case both the velocities here, because they are fixed, have are zeros. So, u essentially the velocity close to both the plates, okay, upper and the lower plates are both the zeros in this case. So, u equal to 0 here, u equal to 0 here, okay, both the planes essentially have zones of no slip. So, in that case at y equal to plus h, u becomes 1 by 2n del p by del x square of h c1h plus c2, and that is 0, and at y equal to minus h, u becomes 1 by 2n del p by del x h square minus c2h c1h plus c2 is also equal to 0. Okay. So, So therefore, the only way you could so you have to decipher what the C1 and C2 are in this particular case. So from these two equations you essentially have two unknowns and two different equations. So it's a set of linear equations and you can solve them to find the C1 C2. So in this case the C1 comes out to be equal to 0 and C2 comes out to be equal to minus 1 by 2 eta delta p by delta x h square by 2. Okay. So if you put the C1 C2 values back into this particular equation here, you finally get the final form of the equation as uy equal to 1 by 2 eta with a minus sign del p by del x, which is the pressure gradient, times h square to 1 minus y square by h square. Alright. So if you plot this equation, it's really the equation of a parabola, because the u is varying as the square of y. Okay. So essentially if you look at the flow profile here within this particular channel that I would be just drawing in about a minute. So you have two fixed plates here, right, and you have central axes, you have y equal to 0 along this, y is plus h here, y is minus h here, and so essentially it's a parabola. So uy is varying as the square of y. Okay. So essentially you can draw the profile something like a parabola where there is a zone of no slip, v u is 0 here, and there is another zone of no slip here, and this profile here is the flow profile of a parabola with velocities, okay, starting from y equal to 0 to y equal to plus h and y equal to minus h. Okay. And u0 at y equals 0 would really be equal to minus 1 by 2 neta del p by del x h square is also the maximum velocity, as in this particular case. You can see the parabola kind of has a point of inflection here where the slope changes, and so the maxima here in this case is corresponding to y equal to 0, and the u maxima comes out to be minus 1 by 2 eta dp by dx h square. Okay. So if you assume a different sign convention, a different spatial location in a manner as if let us say this 2h term, this whole 2h term here that you get as a dimension or the diameter of the capillary is equated to something like a, so that h is a by 2. So in that case the u max would just be written differently as 1 by 8 eta del p by del x times the square of a, where a is the diameter. Okay. So circular cross section of a diameter a would essentially give a u max which is equal to minus 1 by 8 eta del p by del x into a square. Okay. A is the diameter of this particular capillary. So let us now try to calculate the volume flow rate, because this would be important from perspective of later on trying to integrate that onto the electroosmotic flow equation. Okay. And we can also compare the pressure driven flow with respect to the electroosmotic flow, which was really the objective. And in terms of profile, as you will find out in just about a little bit, the electrokinetic flow is really, or the electroosmotic flow is really a plug like flow as opposed to the parabolic flow which is introduced by the pressure driven flow. So basically this brings us to the end of this particular lecture. The next lecture we will be talking more about how to integrate this pressure driven flow kinetics and especially the flow rate with the electroosmotic flows, and then we will also be beaming into streaming potential as essentially EMF caused by velocity of motion of a charged layer with respect to a surface. Okay, thank you.